With our final lesson in Module 8, we're going to be looking at 8.5, titled Solving Special Systems. And in this lesson, our goal is to learn to identify if a system of equations is a special case or not. And if it is a special case, we want to then be able to determine if the answer to our system is no solutions or infinitely many solutions. Now, throughout this module, when we've been going ahead and solving systems of equations, there's primarily been two different types of problems that we've been dealing with. We've been either dealing with a system in which we had to solve it using graphing, where we would graph two lines and then identify the coordinates of where the 2 points intersected, or we would solve it algebraically. And if we solved it algebraically, we would be using either substitution or we would be using elimination. Okay, so what I want to do is take some time to go over what a special system would look like graphically and what it would look like algebraically. So let's go ahead and take a look at a few examples. Alright, so when it comes to graphing special cases, so this is when you've got your graph paper, you've got your two equations in front of you, and you're asked to graph them and determine how many solutions the system has. Now, if the only thing the problem is asking you is if you need to determine if the system has one solution, no solutions, or infinitely many solutions, and it's not asking you for a specific solution, you should be able to determine the answer just by looking at the y-intercept and at the slope. So if you have a system whose graphs has equal y-intercepts but different slopes, it's going to have one solution. Okay? Anytime you have different slopes, you're going to have one solution. Okay? So it doesn't matter if the y-intercepts are equal or not. If your slopes are not equal to each other, you're going to have one solution. So you'd graph those two equations and you would find the single point where the two lines intersect. That will happen every single time your slopes are not equal to each other. So essentially, in order to determine if you have a special case, you're looking primarily at the slopes. Okay, write that down. Look at the slopes to determine if the system is a special case. If the slopes are equal, it is going to be a special case. If the slopes are not equal, it is not going to be a special case and you're going to have one solution. Now, once you determine that the slopes are equal, then you have to determine if your answer is no solutions or infinitely many solutions. Now, in order to determine if you have no solutions, you want to look at the y-intercepts. If a system has different y-intercepts, it's going to have no solutions. On the other hand, if you have a graph or a system with equal y-intercepts, you're going to have infinitely many solutions. So again, first condition, slopes have to be equal for it to be a special case. Then after that, you look at the y-intercepts. If the y-intercepts are different, it's going to be no solutions. If the y-intercepts are equal, it's going to be infinitely many solutions. And here's what those graphs would actually look like. So if they give you a graph with lines on it and ask you to determine if the solutions would be no solution, infinitely many solutions, or one solution, you're looking at the relationship between the lines. And I want you to write this down too. If the lines are parallel, your answer is no solution. So if your lines look something like this, if your lines look like this, those are parallel lines, or at least they're supposed to be. Those lines will never intersect. And so that is no solution, because again, the purpose of a system of equation is to determine where a pair of lines are going to intersect. These two lines will never intersect, and so this has no solution. So again, parallel lines means no solution. Get that written down. For your next special case is going to be one solution. So in order to determine if a system has one solution, again, you're looking at the relationship between the lines. And essentially what's going to happen is you're going to have one line overlap another line. It'll overlap completely and look something like this. So say I've got my first line looks like this, and then you go to graph your second line and you realize that your second line is directly on top of the first line that you just graphed. If that happens, that is infinitely many solutions. With a system of equation, you're trying to determine the point where the lines intersect. With these two lines, they intersect everywhere. At every single point where the line is, those lines are intersecting. So that's going to be infinitely many solutions. Okay? So write this down as well. For infinitely many solutions, the lines overlap. Now let's just say that we're given a problem where we have one line that looks kind of like this, and then another line that looks kind of like that. Okay? Now, clearly those lines don't intersect, but it should also be clear that those two lines are not parallel either. Okay? So, because these lines are not parallel, at some point they will intersect. If I were to extend these lines out and try and make them look somewhat good, we'd see that eventually they would intersect. Okay? So just because two lines don't intersect on the graph that you have doesn't mean that they're not going to intersect at some point. They have to be parallel in order for them to never intersect. Okay? So again, it's only parallel lines that is going to be no solutions. Alright, so let's start look at graphing special cases. Again, that's graphing. Now I want to take a look at determining if it's a special case using our algebraic methods. That's substitution or elimination. Now, in order for it to be an algebraic special case, in order for the system to be an algebraic special case, again, we're using substitution or elimination. It does not matter which one. In order for it to be a special case, both the x and y variable must cancel out. Okay? So you do some math and you get to the point where one of your variables cancels out, and then you realize you do some more math and your other variable cancels out as well. And you're left without any variables in the problem. If that happens, you know you're dealing with a special case. So again, in order for it to be an algebraic special case, both of the variables must cancel. So your x variable and your y variable, they must both cancel out. And when that happens, again, you know you're dealing with a special case. So you're left with just some numbers. Your variables are gone, you're left with some numbers. If the numbers you have left are equal to each other, then it's going to be infinitely many solutions. All right, so again, variables cancel on both sides. If the numbers that remain are equal, that means the answer is infinitely many solutions. And an example of that would be something like you get done with your problem and -3 equals -3. If that happens, that is infinitely many solutions. If it's 17 equals 17 or 52 equals 52, if the two numbers are equal, then it's infinitely many solutions. However, if your numbers are not equal to each other, that's going to be no solutions. So again, if the numbers that remain are not equal, that means the answer is no solutions. So you get an answer something like 8 is equal to 7, or 15 is equal to -2, something like that, where you get numbers that are not equal to each other being set equal to each other at the bottom of the problem. That's not true, so your answer is going to be no solutions. Okay? Alright, so just to recap, for infinitely many solutions, you can determine if a problem has infinitely many solutions by graphing it, and if the lines overlap, that means infinitely many solutions. Or if you solve it algebraically and you get a number equal to itself, again, that means infinitely many solutions. However, if you know that you have a special case, for no solutions, you can get that by graphing if the lines end up being parallel. Parallel lines mean no solution. Or if you solve it algebraically and get a number equal to a number that it's not equal to, that's going to be no solutions. Guys, that's all we've got for 8.5. It was a quicker lesson. Hopefully we understand how to determine if we have a special case or not. Again, for graphing, that's if the slopes are equal. For algebraic method of using substitution or elimination, there really is no shortcut like there is for graphing. We just have to work through the problem, and if we get to the point where the two variables in the problem cancel, we know we have a special case. Now, once we determine we have a special case, we then have to find out if our final answer is going to be no solutions or infinitely many solutions. Email me with any questions that you might have regarding this lesson or anything with Module 8 at all, and I would be happy to help you out and answer your questions so that you can make sure that you have full understanding of this lesson and the entire module's material before we have our assessment at the end of the week. Hope you guys have a good day, and I'll see you back here next time.